Good evening, everyone. My name is Sam, and I'm a PhD researcher at the University of Bristol, and my research centers around the use of robotic manipulators for nuclear inspection challenges.
Thanks, Sam. So I'm also a PhD student at the University of Bristol. My name is Matt, but my research is about using ground-based mobile robots for radiation detecting and radiation mapping.
So sadly, some of you may have seen our last demo, but unfortunately we have some technical issues which have led to the robot breaking. Essentially, the cable at the back snapped, and so we have a problem. That means that we're not able to show you a full demo today. I'm very sorry about that. But that's science, you know, it happens to everyone from the school science project right up to big institutions like NASA. So just the way things go sometimes. But instead, we thought we'd talk to you a little bit about the National Nuclear User Facility, what it is, what it means, and what equipment's available. So the National Nuclear User Facility is where we're stood right now. This is the Hot Robotics Department, which is at the University of Bristol, Fenswood Farm facility. So that's where we are right now. And so we have all sorts of robotic equipment, everything from robot arms to ground-based vehicles to different sensor equipment and drones and even more, which is all available for people to hire, anybody from academia or the industry can hire out this equipment for nuclear research. So I think Matt's best placed to speak about tracked vehicles.
Great. Thanks, Sam. So what you're seeing in front of you is two pieces of equipment we've combined. You have the UK-RAS on the top, and we have the SuperDroid HG2 on the bottom. So the SuperDroid HG2 is a heavy-duty all-terrain tracked robot, which means it's ideal for carrying large payloads like the Kuki you see on top of it. But there's several other platforms that we have for NUF. We have two other wheeled ground-based robots. We have the Leo rovers, which are very small, lightweight, don't weigh more than about 8 kilos, which are good for going inside small areas. We also have a ClearPath Husky, which is a much more substantial wheeled robot, which can carry similar sized payloads to the SuperDroid. We also have a small quadruped robot, which you see in the background, the Unitary A1. So quadruped robots are great for radiation mapping challenges because due to their small foot size, they pick up very little radioactive dust, which makes them well suited for areas with large amounts of contaminated dust on the floor. So how do you like it to Sam?
Yeah, so I'm going to talk a little bit about robot arms. So here as part of the National Nuclear User Facility, we have two KUKA EWA LBR arms. These are great arms. They're force torque sensitive. So in every joint, there's a force torque sensor, which means it can sense things in its surroundings. This means it can be used for human-robot interaction. So it's actually human safe. Because of the highly sensitive force torque sensors, it will detect any collisions that it makes. More specifically for nuclear applications, it's possible that you could use one in a glove box setting, for example, where you've got quite tight confined space to work in, and you might want to avoid collisions or causing damage to that confined space. We were hoping to use it as a mounting on the SuperDroid as part of our combined radioactive dispersal event device, which would allow us to actually manipulate it from on top of the SuperDroid. So the SuperDroid could drive up somewhere and the robot could then sense around its surroundings to find hot particles, for example. And it can do that because it's a very lightweight robot weighing in at just 20 kilos. Otherwise, we have some Canova robots. They're very similar to this. They're a bit more lightweight, in fact, and slender enough to, in fact, to fit through current glove box ports. So alongside the robot arms, we have a range of sensing equipment. So we have a raft of radiation detectors. We have some scintillator detectors. We have the Chromex Sigma, which uses a cesium iodide, a thallium-doped cesium iodide crystal. And the way it works is when gamma radiation hits the crystal, it causes it to glow. And you can measure that glow effect to determine how much radiation's in your environment. We also have an XRF, a portable XRF, which we have mounted on the robot arm system before, and that uses X-rays to actually determine what material you're looking at. Works best in the transition metals, And it can actually, if you're looking at an aluminium pipe, it will tell you it's aluminium. That's, again, available to hire. We also have some Raman probes as well. So one thing XRF is not very good for is actually searching for plastics and very light elements, but Raman is really effective for that. Raman uses laser light to actually detect the electronic emissions, which it feeds back, and from that resonance, it determines exactly what material we're looking at. So I mentioned as well, we have some drone systems. We have, do you know the names of the drone systems?
Yeah, thank you very much. So there are a few different types of drones. The notable ones are the Mavic Pro, which is a lightweight drone, great for doing aerial surveys, because it's got a very good camera on it. We also have some different DJI drones from the M series, including the M600, which is a much heavier drone, which is great for carrying sensor payloads to perform different types of research. So I think now we should be able to show you some footage from earlier of our dress rehearsal, which should still show you parts of our demonstration. So we'll see if we can get that running for you, so you can see what we would have shown you today if you hadn't had some technical mishaps.
Yeah, so just to give you some background, I didn't mention this at the start, but obviously we've mounted the KUKA LBR arm on the SuperDroid with an attached sensor rack. And the idea was that we'd be able to sense radiation on a ground-based, on the ground using the SuperDroid robot with a scintillator detector attached. And then when we identified the hotspot, we would then use the robot arm to actually explore that space in more detail. So that's what you'll hopefully see on our live demonstration. It should be noted that the SuperDroid is a very... Are we live? Platform. Good evening, everybody, and welcome to sunny Bristol. On the floor, you can see that behind us, and so it is able to drive over the top of that as well. A facility where you can hire out all kinds of different robotic equipment. That's everything from robotic arms to ground-based robots, to drones, and even different detector and sensor capabilities as well. So it's all available for you to hire if you're a researcher or industry partner. So to introduce myself, I'm Sam White, and I'm a PhD researcher here at the University of Bristol, and I research the use of robotic manipulators to perform different nuclear inspection tasks. I'm now going to hand over to my colleague.
Thanks, Sam. Good evening. I'm Matthew Ryan Tucker. I'm also a PhD student at the University of Bristol, but my focus is on using ground-based robots to detect radiation and find hot particles. So what we've got here is a combination of two major pieces of an NUF kit. We have the HT2 robot made by SuperDroid Robotics, which is an all-terrain robot, it's a quite heavyweight robot with a payload of up to 40 kilos, and it has several sensors built in, including a laser on the front, which is the Velodyne Puck LiDAR. This LiDAR allows it to build up a detailed 3D map of its world and traverse around it. So Sam's going to talk to you about the arm that we have mounted on top.
Yes, so we have the KUKA LBR EWA robot arm mounted on top. That's a lightweight, even though it's still 23 kilos, lightweight robot arm with a collaborative capability. This means you can perform different human and robot interaction tasks, making it human safe, down to the force torque sensors which are present in each joint. This enables it to detect its surroundings and stop if it detects a collision. This makes it perfect for something like the challenge that we're trying to achieve here, where we're trying to look for the strongest source in an environment, the strongest radioactive source, that is. And we have a radiation detector on the front, which again is available via NNUF, which is the Sigma 50 scintillator detector for detecting radiation. So as we move the robot around in the environment, we can sense the radioactive or hot particles that might be in a given room. So we've combined the two robot systems in order to do that within the space of the facility. So the idea behind our demonstration today is to be able to drive around the room, identify a hot location, that's a space where there's a high level of radiation, and then perform a fine tooth comb scan with the robot arm to identify exactly where that is situated within a wall or elsewhere. In this case, we have a radioactive source at the back there on the wall.
Great. So as you can see on my screen now, the kind of environments that you might deploy these robots in are often quite complicated. This is the Pridnoprovsky chemical plant in eastern Ukraine, which is an abandoned chemical processing facility, which is very radioactive. So you can see on the floor there's all sorts of debris and metalwork and bricks and so on, which can be quite hard for most conventional robots to move across. So this is where robots like the Superdroid HG2 really excel. Because of its tracks, it can travel over small obstacles and even travel upstairs. So you'll see on the floor here we have a few collected bits of debris that we're going to use to demonstrate how the Superdroid with the arm on top can traverse it without any problems. So I'll hand over to Sam.
So I'm going to step aside now. And Matt is going to demonstrate the robot moving across this debris. So as you can see, without too many issues, it's able to traverse across this pile of scrap metal, which is not too dissimilar from the PCHP plant that Matt mentioned earlier. Okay, so that was a nice demonstration of its capability to really drive over really rough environments. So I'm going to pass over to Matt now.
Great. So what you'll see here on my screen again is, well, as we've got a really detailed view of how the robot sees the world. So we have these multicolored points represent the point clouds that the robot is building up with its LiDAR. We also have a 2D map, which allows us to see obstacles marked out in black. Now, these colored spheres here that you see represent the counts per second of the picked up by the radiation detector. And you'll see as we move the robot around the space, it populates more of the area with these colored spheres. Now, if the spheres are yellow in color, that implies there's not much radiation around. If the spheres are greener in color or bluer in color, that implies it's a higher radiation count. So you see here, we have got a peak in this corner over here, which is getting close to where we store our sources in a safe in this corner. But we have another peak just around here. So we can move over to that point and we can create a radiation map of the area in more detail using the KUKA arm that is on top of it.
Yeah, so the KUKA arm can now position itself up against the wall. So the arm itself recognizes and has been told by the Superdroid that it should scan to its left. So now the system begins to move the arm right over to where it's required on the wall there, where we have our radioactive source, because we identified that hotspot that Matt showed us on the visualization screen. So the arm begins by lining itself up to the wall. We'll just wait whilst the arm does that. And then it's going to start moving across the wall, collecting a radiation measurement at every point and combining that with the positional output of the robot arm itself, from which we can generate a rather similar radiation map to the one that Matt created from moving the robot around on the floor. So you should start to see now the positions from the robot arm populate the wall, which is shown on the RViz screen. So there you see the first one's green, because we're not pointing directly at the source yet, and we've got a relatively low radiation count. And then as we move closer to looking at the source, we start to see a population of bluer spots. Now, this is really a useful tool for using in an extreme environment or an environment where you might want to send a person in if you're unsure about whether it might be safe. Because the robot can go in, it can work out where the radioactive hotspots are located, and then it can scan over them to ascertain whether or not the space is safe for humans. You could also very easily mount other sensor systems on the arm if you're worried about, for example, asbestos being present in the room. You could integrate, therefore, something called a Raman sensor, which uses laser light to identify different materials. And that could be used to point out hazardous materials, not just radioactive materials. So the arm's just going to continue to sweep across there and build up that radiation map.
You can also see one of the key advantages of using the robot operating system, or ROS, with this visualization. So in this case, we have four different computers that are doing different elements of processing sensor data or controlling the robot, but it can all be combined into one visualization with an incredibly low latency, and it allows you to combine all of these different sensor inputs to get a detailed map of your environment, both from a physical point of view, but also from the radiation point of view, as you can see from these colored spheres here.
Okay, that's great. I think that more or less concludes our demo today. So thank you very much for coming along and attending. Thank you very much for coming along and attending. And hopefully we'll see you at the National Nuclear User Facility sometime soon. Come on, Matt. system begins unfortunately, so you'll see our dress rehearsal of this demo because we had some technical difficulties in the first test. Now this is unfortunate, but I guess it's just how science goes sometimes. So on the front of our demo system, we had mounted a radiation detector, also available via NNUF. That's the Chromex Sigma cesium iodide or thallium doped cesium iodide crystal, which glows in the presence of radiation. So we're able to detect how much radiation is in its environment. So we've combined the SuperDroid and the KUKA system here so that we can actually explore the environment. We can drive around and identify dangerous or hot particles. So one purpose for this, it could be after a radioactive dispersal event. Now that could be a small laboratory accident somewhere like Sellafield, or it could be something as extreme as a radioactive disaster such as Chernobyl or Fukushima. And the idea is that the robot could explore its environment and scan and search out for hot particles. So in this instance, we have a room, you'll see in a moment, where we're attempting to search for that strong source. So I'm going to hand over to Matt now, who's going to speak a little bit about the advantages of the SuperDroid in such a space.
Thank you. So the kind of environments where this might be deployed aren't always clean and simple. There's often various obstacles around. You should see on the screen now a picture of the Prinopovsky chemical plant in eastern Ukraine. As you should be able to see soon, it's covered in debris all over the floors with like girders, rubble, tiles, all of which have fallen on the floor. Unfortunately, we're having technical difficulties, so we won't be able to show you that picture either, but we've recreated it for you in our own lab with this pile of miscellaneous debris. So I'm going to hand the microphone over to Sam, and I'll demonstrate the fact that your training capabilities of the SuperDroid, combined with the positioning of the KUKA, making sure its center of mass is directly above the SuperDroid, means that it can traverse these kind of obstacles without any major issues.
Cool, thanks for that, Matt. Yeah, so Matt's just off to grab the controller for the SuperDroid. So as you can see behind me, we have a piece of a gate, we have some random bits of metal, a table, we have a manhole cover, all things that might be present in such a scenario. So obviously there's a few different robots out there that are capable of driving around across factory smooth floors, but the idea of this is to demonstrate how it can tackle such an extreme environment. So Matt's going to spin it around now. And it's just going to drive right on over the debris that we have on the floor there. I never get bored of watching it do that. It's always great fun. So pass over back to Matt, who's going to talk a little bit about the radiation mapping procedure.
Cool. Do we have the screen shown? Okay, so I'm going to grab that GoPro so I can show them what everyone's seeing. You need to bring up the screen as well. We have these multicolored points which represent the walls, which are picked up by its LiDAR sensor. And you'll see these colored spheres on the floor represent the count per second from the radiation sensor. So now this can be driven around the floor of an environment to gradually build up a detailed map of whatever is there. So you see there's a little bit of noise in the middle of the map from samurai walking around, but that's the kind of thing that can easily be fixed in post-processing. Now at the moment I'm controlling this, but it would be possible to do this autonomously if it was a simple area and you weren't too concerned about prospects of running things over. Now the Seeker would be fine with that, but it might occasionally damage things on the floor. And so you'll see here that, oh, that's not a straight line. You'll see here that you can gradually start covering the entirety of the space with these colored dots. Now I think now we're going to cut over to our pre-recorded rehearsal, and we should be able to show you the KUKA arm mapping the wall.
To move the arm right over to where it's required on the wall there, where we have our radioactive source, because we identified that hotspot that Matt showed us on the visualization screen. So the arm begins by lining itself up to the wall. We'll just wait whilst the arm does that. And then it's going to start moving across the wall, collecting a radiation measurement at every point, and combining that with the positional output of the robot arm itself, from which we can generate a rather similar radiation map to the one that Matt created from moving the robot around on the floor. So you should start to see now the positions from the robot arm populate the wall, which is shown on the RViz screen. So there you see the first one's green, because we're not pointing directly at the source yet, and we've got a relatively low radiation count. And then as we move closer to looking at the source, we start to see a population of bluer spots. Now, this is really a useful tool for using in an extreme environment or an environment where you might want to send a person in if you're unsure about whether it might be safe. Because the robot can go in, it can work out where the radioactive hotspots are located, and then it can scan over them to ascertain whether or not the space is safe for humans. You could also very easily mount other sensor systems on the arm if you're worried about, for example, asbestos being present in the room. You could integrate, therefore, something called a Raman sensor, which uses laser light to identify different materials. And that could be used to point out hazardous materials, not just radioactive materials. So the arm's just going to continue to sweep across there and build up that radiation map.
You can also see one of the key advantages of using the robot operating system, or ROS, with this visualization. So in this case, we have four different computers that are doing different elements of processing sensor data or controlling the robot, but it can all be combined into one visualization with an incredibly low latency, and it allows you to combine all of these different sensor inputs to get a detailed map of your environment, both from a physical point of view, but also from the radiation point of view, as you can see from these colored spheres here.
Okay, that's great. I think that more or less concludes our demo today. So thank you very much for coming along and attending. Thank you very much for coming along and attending. And hopefully we'll see you at the National Nuclear User Facility sometime soon. I think that more or less concludes the demo. So if we roll back to the camera, hope you can all see me. and I'll be very happy to take any questions you may have. Please don't be shy, fire away.
I have a question.
Yes.
So, when would you? Are you doing research on this sort of system at the moment? Is this part of your current research?
Yes. So if in case you missed that, the question was, is this part of my current research? And yes, absolutely. So Matt and myself have been working on this system, and we're hoping to eventually deploy it in Chernobyl. So obviously we've got a few things to iron out, as you might have guessed from our demo, but we are hoping to send it into the facility there, under the dome, as it were, to actually identify hot particles in rooms where they're a bit uncertain about whether they might be safe for humans.
I have another question. So how is this really useful to use in a place such as Chernobyl? What is it about the environment of Chernobyl that makes this ideal robotic system to use?
Okay, so the question was, what makes this specifically ideal for an environment such as Chernobyl? And I suppose the answer, well, Matt, would you like to take this one, or should I? Or?
Thanks, Sam. So I'll budge over Sam in frame. There's a few things that make this quite useful for deployment in Chernobyl. So one of the things they'd be interested in doing with a robotic arm in Chernobyl would be to drill holes in surfaces. So the fact that this arm has got force feedback means it would be ideal for that, because it'd be able to respond to how much resistance is going from the material and make sure it didn't just snap the drill bit. Also, the fact that it's a fairly all-terrain robot is very advantageous. It can travel upstairs with its tracks, which would mean that it can travel through all sorts of obstacles that might be inside the the sarcophagus. The fact that we can also mount a huge array of radiation sensors on it and move them around on the end of the arm means you can get really detailed information about the exact sources of radiation and use that to characterize different environments.
Cool, great, nice answer, Matt. Thanks.
Is this a first then, going under the dome, the sarcophagus, since the incident?
So I think Matt's the best place for that.
So they've sent a variety of robots developed in the Soviet Union and in Ukraine under inside the sarcophagus, but they have not yet sent many robots that have been developed in Europe or the United States. So we currently don't have any dates about when this might be taken over to Chernobyl for that kind of deployment. But a team from the University of Bristol will be traveling out there in September to deploy some other technologies. So we will be making sure we let them know what we developed here and see if they have any possible uses for it.
Nice one.
Last question from me. So you mentioned there that in September the team will be taking other pieces of kit over to Chernobyl. What sort of piece of equipment might that be, and how will they be used?
Yeah, so again, sorry, I'm not on best trip, so.
Yep, so there's a few pieces of equipment we'll be taking over. So we'll be taking over a selection of drones for doing outdoor radiation mapping. But we're also planning on taking out a Boston Dynamics spot, which we'll get through the NNUF access scheme from RACE, which is which is one of the partners of the National Nuclear Facility based in Culham in Oxford. So we'll be taking out that platform paired with some sensing equipment from a team at the University of Oxford, and we'll be using that to create detailed 3D maps of the inside of various buildings around the Chernobyl site, with the goal of eventually, on the end of the trip, deploying once or twice inside the sarcophagus itself.
That's really exciting. So let's talk about sort and seg. How are these KUKA arms? I understand they're used in the automotive industry, but obviously there is a range which are used within nuclear and could be used to sort nuclear waste. So are these KUKAs designed for that?
Yeah, so the question was on KUKAs and what they're designed for and what their potential applications might be, particularly around nuclear waste sorting. So the answer to that is yes, as you mentioned, the KUKA arms are primarily used for the automotive industry in manufacturing. But that's the more larger industrial arms, which you see from time to time on the news. So you're probably quite familiar with those. An arm like this, a collaborative arm, represents more of a research-based arm. I mean, at the moment, there's not too many industrial applications for collaborative arms. But it's quite a very exciting time to explore what they're capable of. You've got lots of people working with human-robot interaction. I think the University of Manchester are showcasing that today, and also, you know, using the force feedback for applications such as drilling. But I think that yes. So one aspect of my research, obviously, I'm using a lot of different sensors such as XRF and Raman probes and radiation detectors on the end of robot arms, with a view to be able to sort and distinguish between different waste items ahead of their long-term disposal. Now, one of the key advantages of using a collaborative arm in doing that is actually the force feedback allows you to actually weigh objects in situ. So the nuclear industry is very conservative, and they like to know precisely the weight and the classification of a material. So anything that you could use to sense out different materials and then weigh the object is very sought after.
Great. In that case, I think we'll take an early break to reset the next demo at 5:30.
Yes, so as I say, any questions, feel free to point to us at, you can find us online at the University of Bristol, the National Nuclear User Facility, Hot Robotics. Yeah, please feel free to ask any questions, but thank you for now, and I'll see you after the break. Good evening, everybody. You join us here in sunny Bristol for our live demonstration. You join us here at the National Nuclear User Facility, Hot Robotics Department, here at the University of Bristol. So the National Nuclear User Facility, or NNUF, is a large conglomerate of groups, and the Hot Robotics Department is one of those, and they allow for the hiring of robotic and technical equipment to both industry and research and industry and academia for nuclear research. So we have a range of robotic equipment available. We have robot arms, we have tracked robot platforms, we have a range of different sensors, including radiation sensors and XRF, and we also have a variety of drones as well. So my name is Sam White, and I'm a PhD student here at the University of Bristol, and my research centers around the use of robotic manipulators for nuclear inspection.
Thanks, Sam. Like Sam, I'm also a PhD student. My name is Matt, and I focus on ground-based mobile robots for radiation mapping and particle localization. So what we have here is a combination of two bits of NNUF kit. We have the KUKA arm on the top and the SuperDroid HD2 on the bottom. So the SuperDroid HD2 is an all-terrain tracked robot with a heavy payload of around 45 kilos. It's got a built-in LiDAR, in this case the Teledyne puck, which has 16 lasers which spin around and allow it to build up a detailed 3D map of the world. So the fact that it's an all-terrain robot and the fact that it has a high payload means it's great for carrying something like the KUKA arm, which Sam is going to tell you slightly more about.
Yeah, so this is a KUKA LBR-EWA collaborative robot arm, which we've mounted on the top of the SuperDroid. One of the key advantages of the LBR arm is the fact that it has force torque sensors in every joint. And this can be used for human-robot interaction, as it senses its surroundings very carefully, so it knows if a person is present. For our users, it can be used to detect its environment. So if it detects a collision with a wall, for example, it will stop. And that means that we limit the damage that we attain to the system and to the wall itself. So what we have done is we have mounted the KUKA on the SuperDroid in the hope of creating a radioactive dispersal event device. So the idea being we can drive the SuperDroid around an extreme environment and search for hot or dangerous particles. So we have a radiation sensor attached to the robot arm, which senses radiation. And it does that using a thallium-doped cesium iodide scintillation crystal, which glows in the presence of radiation. And you can measure the strength of that glow to determine how much radiation you have present. We have a second radiation detector mounted on the SuperDroid platform itself, and the idea is that it can drive around the room, work out where the hottest, radiation-wise, where the hottest spot is in the room, and then use the robot arm to actually search that out, using the arm to figure out where that is. Maybe it's on a wall, maybe it's on the ceiling, maybe it's somewhere that's not the floor. So our demonstration today, I'm afraid, is cut a little short because we had some technical issues with the robot arm, but we're able still to show off the use of the SuperDroid robot. So the idea of our demo, and you'll see this from our dress rehearsal, which we'll play halfway through, the idea of the demo is to actually search for the most radioactive source within the room. So we start by driving around looking for it, and then we use the robot arm to scan for it on the wall itself. So I'm now going to pass over to Matt, who's going to talk a little bit about the SuperDroid and why it's so good for the use after a radioactive dispersal event.
Great. Thanks, Sam. So the kind of places this robot might be deployed aren't always clean, safe environments. They can have obstacles scattered around the floor, or just general debris which make for a very uneven surface. So there are several robotics platforms which would perform very well in those environments, but not be able to handle, perform very well in flat environments, but not be able to handle mild obstacles. But the SuperDroid is not one of these. You'll see a picture on the screen now of the Penhovsky chemical plant in eastern Ukraine, which is a disused chemical processing facility. As you can see, there's all sorts of bricks, debris, and metalwork scattered around the floor. So the aim of using the SuperDroid for this kind of a project is that it would be able to handle stuff like that without any problems. So behind us, you see an attempt to recreate some of what we had in PCHP. and I'm now going to drag the Superdroid over it to demonstrate that the combination of its all-terrain ability and the positioning of the KUKA such that the center of mass is above the robot means it can handle these kind of obstacles without any issues.
All right, so Matt's just going to go over there and pick up the controller. I'm going to stand back a little bit. And I'm going to watch as the system attempts to drive over our debris. Very well. The noise it's making, you could be forgiven for Cool. So now Matt's going to continue to perform a bit of a radiation map. He's going to scan across the floor, searching for radiation with the Superdroid mounted radiation detector. So I'll hand over to Matt, who will explain that process.
So what we can do is now figure out how the robot sees the world. So what we have here is we have all of these areas.
Yeah. There we go. So now you can see what the robot's seeing. There's a lot of mess in this section here, but that is largely because of Sam and I walking around, and that's the kind of thing that could easily be fixed in post-processing. So you see here that as we move the robot around the space, these colored spheres behind it. Now the color of that sphere is correlated with the number of taps per second that the device picks up. So in doing this, you can travel around an environment and gradually pick up scan of the radiation. Now this is all very uniform because we don't have any sources nearby. If we were to have any sources in the area, you would see that as we get closer to them, the colour starts to change, indicating more taps per second. What you can also see on this map, the two-dimensional base layer is the projected map. So any white spaces on that are assumed to be completely empty. And any black spaces are assumed to have obstacles in. Again, you can see a lot of marks around this map from Sam and I walking around, but that's all the kind of thing that could easily be fixed in post-processing. There we go. So you see now I'm approaching the wall where we would have done our radiation mapping with the arm, but due to some technical difficulties, we'll instead be cutting to a video of our dress rehearsal to show what we would have been doing now. And Sam's going to talk you through.
The system begins to move the arm right over. Goes. There's not a lot you can do about that kind of thing. So anyway, you'll see we cut to a dress rehearsal. There you can see me in the background there, talking you through a previous run that we did. So in an ideal world, we have our radiation sensor, and we manipulate the arm to face the wall. We actually also had a depth camera on there, and the depth camera was able to ensure that we were constantly flush with the wall, as if the Superdroid was parked in a non-ideal position, then it could be the case that you would need to ensure that you were flush with the wall just to keep your radiation readings consistent. So now the KUKA is going to start tracing the wall in a raster scan style pattern, and it's going to pick up radiation data using the sensor, and it's going to combine that with the positional data, which is being offloaded by the arm. And that's going to start to populate the map, which you can see on the right-hand side of your screen, which shows the radiation on the wall. So as you can see, as we get closer to the source, it turns to blue. So blue represents a hot location, and yellow or green represents a weaker location. And as you can see, the arm just continues to trace out that raster scan pattern to search for the source. This could be particularly useful in our environment because, such as Fukushima or Chernobyl, as if there was a room that you weren't sure whether you could send a person into, you could scout out that room. If the radiation level looks safe for on the basis of the SuperDroid map, you might want to just examine the walls to check there's nothing on the walls, doing a sort of finer tooth comb approach, which is what the robot arm enables. And then you might determine that you might not want to send a person into the room, or it may in fact be safe. So the other thing that we can collect from the radiation data is we get a full spectral output from the sensor itself. So every radioisotope emits gamma radiation at different energies, and those energies can be used to tell us a little bit more about the gamma emitter itself. So we'd be able to say whether or not the particular emitting isotope was safe. It might be uranium, it might be plutonium, we just don't know. Cool, so it's finished up that. So it's finished that process. So we'll now revert to have some question time. So you should be able to see me. Just stood behind our SuperDroid, affectionately known as the Super Duper Droid, because it has the arm mounted on the SuperDroid system. Cool. So I had a question come in about how intuitive the controls are. And the answer to that is it varies, really. You can obviously use all of this equipment autonomously, in which case there are no controls. But you can control it with a joystick, such as an Xbox controller or a touchpad. There's a variety of options there. So it depends really on the application is my answer to that question.
Great.
Well, so I'm very happy to answer any more questions. Don't be shy. We're really happy to answer any questions that might arise. And if you don't want to ask a question right now, you're more than welcome to get in touch with us. If you head to the National Nuclear User Facility website, just search on Google National Nuclear User Facility, and it should take you straight there, and you can find some contact details where we'll be more than happy to take any questions you may have. But yeah, so I'll just wait a couple minutes for a few more questions before we sign off.
I hear you'll be deploying equipment in Ukraine. Can you please tell more about what you will be doing? That's the question.
Okay, so we've had a question come in. I think Matt's best place to answer it. Do you want to just tell them what the question is?
Yep. So there's been some talk of deploying the system in Ukraine, which is what the question was about. So if we were deploying it in Ukraine, we'd be taking it to the Chernobyl nuclear power plant, where it could be used to explore rooms which it's difficult to get humans access to. One of the things that we'd be looking at doing if we were to do such a project would be to mount some form of drill on top of the KUKA, which would allow it to drill holes in material and take samples of them. So one of the reasons the KUKA is excellent for that is because it has force feedback, which allows it to pick up information about how the drill would be responding to whatever surface it was in contact with.
Awesome. Thank you, Matt.
What is your favorite robot out of the NUF?
So the question was, what is my favorite bit of kit? So I'll start by answering it, then I'll hand over to Matt. I think my favorite bit of kit is, in fact, this KUKA LBR arm. I've loved working with it throughout the course of my PhD. I think it has a huge amount of potential. I love the force feedback that you get. You can actually run it in what's called compliance mode. So you can actually move it around with your hand, and the KUKA will just follow really loosely. So if you had something heavy you needed to pick up, you could guide the robot and it would be able to fulfill that challenge. Yeah, I've spent a lot of time working with the KUKA. That would have to be my pick.
Great, thanks. I'd say my favorite robot would almost certainly be the SuperDroid, as in it's very, it's very heavy duty, can handle all sorts of terrain, and it comes with a lot of sensors already built in. It's already got an IMU, a GPS, and a LiDAR, which makes
job of anyone doing any research with it much easier, because all you have to do is add your own sensors and then you're good to go. In terms of my favorite sensor that we have, it'd probably be the Hokio two-dimensional LiDARs, just because of the huge amount of data output you get from them. So they collect around 5,400 points every revolution, do 40 revolutions a second, which means that within 5 seconds, you're already up to 1 million points, allowing you to build up really detailed point clouds just from a single two-dimensional LiDAR, which can be really useful for all sorts of mapping where you can't use information from the robot about how far it's traveled.
Awesome. So it's quite a nice system for us both to build and design then. We've got all of our favorite kit combined into one right here.
And ideally, where would you like this to be deployed to show how good an application is for nuclear research?
So the question was, where would we most like to deploy this robot arm to show off its capability for nuclear research? And I think that there's a number of places that spring to mind. I think the most obvious one, and the one we hope to one day deploy it in, is in Chernobyl. You might have seen recently an article about a room that they have there, which is, they're just not sure what's in it. Where it might be safe, it might not be. So the idea for us is to actually use our super droid system here to investigate what might be within that room. And the first step of that requires us to drill a hole through the wall just to get a sort of initial sensor reading of what might be coming through there. So hopefully we'll be able to use a drill mounted onto the KUKA, using that force feedback to ensure that the drill bit does not break, to break through that wall to do an initial assessment. If it's safe enough, it's not going to destroy the robot system, then we'll be able to roll our system through and really learn a bit more about what's in that room.
What are the advantages or disadvantages of combining several off-the-shelf components rather than trying to build a custom robot from scratch?
Yeah, so the question was on combining off-the-shelf equipment versus building a custom design from scratch. And the answer to that is you have a lot of problems that actually arise when you combine different off-the-shelf components. It's not as easy as it might seem. So that is certainly one problem that you face. But the main advantage of it is you have a lot of different equipment which has been verified in the field in different applications. So you have that sort of strong foundation for your research. Yeah, I don't know if Matt's got anything you'd like to add.
Yep, thanks. The advantage of using stuff you can buy off the shelf is simply just the thousands of hours that have gone into it already. So obviously we're both PhD students, which means we have 3.5 years to get all of our research done. So if we were trying to do everything from scratch, you'd be spending a lot of time just doing that. So being able to buy cutting edge equipment, such as the KUKA arm and other different platforms, means we can leverage the advances made in that and use them for our own research more effectively.
Awesome. Nice answer, Matt.
If you were to, of the equipment that isn't here, is there anything in particular that you really want that isn't here?
Good question.
I suppose thinking more broad. So the question was on any equipment that we would like that isn't here. I suppose in an ideal world, you would want to mount as many sensors as you could possibly fit onto the end of the arm to really understand your environment to the maximum possible level. Now, we have actually a few sensors available via NNUF, which we've been able to mount on the system itself, including XRF, portable XRF system, which enables you to perform XRF characterization in the field on a robot arm really easily. There's no need for a benchtop lab system and taking ex situ samples over to your benchtop system away from the lab. So there's that. We also have a Raman probe available, which we'd like to integrate into this system so that we could use it for material characterization as well. So that's one thing. Although they are available to us, it's difficult to mount everything that you need on the end of the arm just for space reasons. So I guess that's my answer. Is anything you'd like to add, Matt? Or?
No, that covers most of it.
It's really, yeah. I suppose that there's a lot of stuff which maybe isn't invented yet, which could be useful, make our lives easier. But we'll get there eventually.
As a final note, then, what would be the ultimate invention that you think would be amazing?
The ultimate invention, I would have to say, is I think my biggest hurdle has been often just the size of some detectors. Like a portable XRF is maybe yay big. It's a sizable bit of kit. I would love for a tiny version of all the sensor equipment that we have, such that it could easily fit on the end of the arm. Anything?
Great, yeah. I think the ultimate invention from the mapping point of view, which does exist, but it's very cumbersome and not very long range, would be a LiDAR that also projects images on what it's detected. So they're used a lot for different building surveying, but it'd be amazing if you could have something the size of Verdine Puck, which also collected picture data and allowed you to not only create a point cloud, but also superimpose what it looks like to create a perfect 3D model, which is something which a lot of research is going on to at the moment.
Very nice. I suppose the last thing might be, obviously, if you're looking at deploying in extreme environments, awesome thing would be to be able to use some drone to actually deploy this system itself. I think, to my knowledge, that the payloads are still quite weak for drones, but maybe one day we can fly this in somewhere. Wouldn't that be awesome?
Great.
Cool. So I guess that's all for questions. Thank you very much for joining us today. It's been a real pleasure working on this project. I'm very sorry about the problem we had, but thank you very much for tuning in. Good night.